So we had x of n, and then we were going to sum, but we're not going to sum over a range stretching to infinity. So let's leave that as is for now. Inside we had ck. ck will still, of course, be there. And then we had the complex exponential, which was j2 pi k. And now we're going to replace the fundamental frequency with 1 over n. And time is going to be replaced by simply small n. So let's take a copy of the discrete plot that we did earlier on and consider the case where we look at the harmonics and how many samples it takes to represent those harmonics. So let's get the plot, paste it, and move it across. And we have the points A to B. This represents our fundamental frequency. And if we now consider the next harmonic of the fundamental, then it will have a period, and that period will be half the period from A to B. So from A to B, I'm marking as yellow lines there, dashed lines, and halfway between those two dashed lines represents the point where we have the first harmonic. So let's just draw a sine wave and roughly say that the period ends halfway, and then consider how many samples do we have to represent that sinusoid or that sine wave. So we have the first sample of the fundamental and this new sinusoid coinciding. Let's use a different color. So there we have our first sample, and we have our second sample, and third, fourth, fifth, we have our sixth, and seventh, and I think that should be enough to represent the period. So we've gone from 13 samples for the fundamental to 7 samples for the next harmonic. Now, if we were to look at the harmonic after this one, where k is equal to 3, for instance, then we would find that the number of samples available to us to represent a complete cycle basically reduces. And so if we continue, then we can see that we reach a point where the number of samples, so I'm just marking the next point for the next harmonic. So we reach a point where the number of samples basically isn't enough to represent a complete cycle, and we will start seeing aliasing at this point. So we mistake real frequencies of a particular value for another, and so there is a limit on the number of harmonics we can have to represent our discrete signal, and that limit is obviously less than infinity. So we're going to use that knowledge to set the range of harmonics that we have available to us. So we're going to replace minus infinity with 0, and plus infinity will of course be replaced as well, and the maximum number of harmonics that we will have is capital N minus 1. So let's copy our equation. This is the key equation, and we will draw a box around it because it is special. Need a better box than that, so let's rub that out. And this is now the synthesis equation for the discrete case. So we started off with the synthesis equation for the continuous case to remind ourselves of what we had said previously, and now we've wrote down the equivalent synthesis equation for the discrete case. Okay, so let's now copy that and begin to think about the next step, which is to consider the analysis equation. Now, hopefully, you will remember my discussion on the analysis equation when I looked at the continuous case. If not, please go back and have a look, review. But basically what I said was that you could take a signal, you could have a view where you take the signal, you compare it with the harmonics one at a time, see how alike they are, and give it a value, a score. And that process, of course, represents correlation. And so we're going to do the same thing here for the discrete case. We're going to consider the correlation of the signal with the set of sinusoids. So to begin that process, let's write down x of n is going to be multiplied by the set of sinusoids. So we're going to write minus j2 pi e to the power of minus j2 pi. Let's replace k with a different variable because we don't want to confuse ourselves. We did the same thing for the continuous case. We're going to use L. And the fundamental frequency is 1 over capital N, and then time has been replaced by small n. And correlation means we multiply these two variables or these two signals together, and then we integrate. In the continuous case, of course, we're dealing with discrete signals, so we sum. And we sum over a period which consists, which is from n, small n, 0 to n minus 1. And this is the correlation, an expression for the correlation. And at the end of evaluating this function, we will get a score of how alike the signal is to the sinusoid. So let's write that down. X car is our measure, which is a function of L. L being the particular harmonic that we are considering. Now let's substitute for xn by making use of the synthesis equation. Again, we are following the same process as we did for the continuous case. So x car, which is a function of L, is equal to the summation from n equals 0 to n minus 1, which means we are summing over the period, we are integrating over the fundamental period. And what we're going to integrate, of course, is xn, which is the same as this expression, which we're going to copy and paste. And we mustn't forget, of course, our exponential function, and we must write that down. So multiply by e to the power of minus j. Now we're going to simplify things. So let's take a copy of this expression and take it to the next page and simplify. So x car, small x there, you need capital X. So capital X car, which is a function of L, is going to equal, well, let's change the summation, put the summation over the harmonics outside, and put the weights outside as well, because they are just a function of the particular harmonic. And then we have the summation over the period, the fundamental period. And now we can also simplify the exponentials, because the exponents will simply add. So we have e to the power of j2 pi, and in brackets we will have k minus L. And 1 over capital N times N is going to be common as well. So now we have a simplified form, and we're going to consider the case where K and L are equal. So what happens when K and L are equal? Well, think about x to the power of 0, because K minus L is 0. X to the power of 0 is always going to be 1. So let's write down the equation. X car, which is a function of L, now this summation is going to be simplified because we're only considering when K is equal to L. So we will get rid of this summation and write down, we will substitute for K with L, so CL. And then the next summation is from n equals 0 to n capital N minus 1, which is the fundamental period. And of course, e to the power of 0 is going to be 1. So we're going to sum all ones. So the final answer is CL times N, capital N. And that's what X car will equal. But of course, we started off by defining X car as a measure of correlation. So let's copy that expression and paste it in here. And let's get rid of the X car there and replace it with simply an equal sign. So CL times N is equal to this expression that we wrote down, which was a measure of the correlation between the signal and the sinusoids. Let's get CL on its own by shifting 1 over N, N to the other side by making it 1 over N. And now we're basically there. We have an expression for CL in terms of the signal, the discrete signal, and a set of harmonically related sinusoids. So here's the synthesis equation which we derived earlier on. And we're also going to put down the analysis equation. And the analysis equation allows us to calculate the values of those weights. So if we know the discrete signal, we can calculate the weights. And this is known as the analysis equation. So we are there. We need to replace L with K. But we have derived the key equations. Now I have missed a step out. I considered the case where K is equal to L, but I did not consider the case where K is not equal to L. And the reason why I didn't cover it is because I did cover that particular point when I considered the continuous signal, and so I would say that it would be useful if you listened to those 4 sets of videos on the continuous signal, because basically the answer is the same, which is when K is not equal to L, then the answer is 0, and we can basically ignore that particular case. Thank you for listening.